In this video, we're going to introduce the law of total probability through another Bayes rule problem. So let's set up our problem first. Suppose I have three types of coins. So coin 1, the probability of getting heads, probability of heads is 90%. Type 2 coins, the probability of heads is 50%. And then type 3 coins, the probability of getting heads is 20%. Now, suppose that I have a bag of coins. So let's draw a little bag. There we go. It's got coins inside of it. Nice, shiny coins. Look at all those coins. And the probability of getting a coin biased 90% towards heads, so the probability of getting a coin of type 1 is 20%. The probability of getting a fair coin is 50%. And the probability of getting a coin biased towards tails is, well, we have 20%, 50%, 30%. So if we write these guys formally in terms of conditional probability, this is telling us that the probability of heads given getting a coin of type 1 is 0.9. And then we can just write the same thing for the other types of coins. And you see, I think you see where this is going. We're now going to ask, if we flip the coin and get heads, what is the probability of the different types of coins? So now let's say I did reach into this bag over here, and I flipped a coin, and it did indeed come up heads. And so what is the probability that I drew one of the biased coins? So now we're asking the question, what is the probability that I drew a coin of type 1 given that I flipped a head? Well, we'll write that out using Bayes' rule. So I can flip this conditional probability around first. So that's the probability of heads given getting a coin of the first type times the probability that I got a coin of the first type divided by the probability of getting heads. Oh, well, we don't have this information, but we can figure it out. So how do we figure this out? How do I figure out the probability, the overall probability of getting heads? Well, if I draw out my sample space, there's some probability of getting heads. And then we also know that I got one of the three types of coins. So maybe this is coin 1. You know, this is definitely not the scale. You know, this is, I don't know, coin 2. And then maybe this is coin 3's region over here. So what do we see here? We see that we must have either gotten this type of coin, this type of coin, or this type of coin, and we must have either gotten heads or tails. So we say that the three types of coins form a partition of our space omega, because if I'm in omega, I had to draw one of these three types of coins. Now, looking at this, well, some of the heads area is in here, some of it's in here, and some of it's in here. So we could write the probability of heads is equal to the probability of heads and coin 1 plus the probability of heads and coin 2 plus the probability of heads and coin 3. And now we can do this using our addition axiom about probability, because all of these events are disjoint. I have to have either been in here, here, or here. So I can sum up the probabilities. Well, what do we do with these? I don't know the intersections directly. This is nice, but what's the next thing I can do? Well, if we remember our Bayes rule, or the factorization that led to Bayes rule, we can break up each of these probabilities in terms of things we know. So for example, this is equal to, well, it's and the intersection here, so I can just factor that as the probability of H given C1 times the probability of C1. And I can do the same thing for the other two. Let's take this. So this is the probability of H given C2, probability of C2. So now, and then I would just do the same for the third. So now we can actually compute this in terms of things that we know. So this whole term over here, well, this is 0.9 times 0.2 plus 0.5 times, what's this, 0.5 plus 0.1 times 0.3. And then we can work out what this actually is. So this is equal to 0.18 plus 0.25 plus 0.03 equals 0.46, which is more or less what we would expect, because the coin biased towards tails is slightly more likely to come up than the coin biased towards heads. Okay, so now we have this, so now we'll just plug everything in to our Bayes rule over here, and the probability of heads given coin 1, that's 0.9, so we have 0.9. Let's use a more fun color, I don't know why. 0.9 times 0.2 divided by 0.46. And this works out to approximately 0.391. I just paused the video and did it in the calculator. I wish I could do it in my head that fast. So, generally speaking, what have we learned here? We've used the law of total probability to solve a Bayes rule problem. So in general, the law of total probability states that if I have a partition, A1 through AN, A1 through AN, partition, so what a partition means is that the union over all the AI, where I goes from 1 to N, and that's equal to omega. If I have this, then the probability of some event B, I can just break it up into the pieces of B that intersect each of these. So this is now the sum, I equals 1 to N, of the probability of A, I, and B. And then, from here, you can use our factorization to turn these intersections into conditional probabilities, which are usually the piece of information that we'll have that we can actually compute something in. One point to note is that maybe I have some AIs and they don't all add up to the whole space, but as long as they cover B entirely, so if I have something like this, So this is B in here. And then maybe I have, one set out here, another set out here, another set out here, and then I have an extra piece out here. Well, I could use all of them, but I don't have to because the intersection of B with this guy out here is just 0, so it's not going to contribute anything to the sum. So that is the law of total probability, and you're going to be using that a lot with Bayes' rule problems because it's frequently how you're going to find the denominator in the problem.